Let's go back to considering the wavelengths of different objects. We considered a baseball, but let's also think about now an electron. And an electron is something where, in fact, we might be able to, if we calculate it and see how that works out, actually observe some of its wave-like properties. So if we do this calculation for an electron, saying it moves at 10 to the 5th meters per second, then what we end up with for a wavelength is 7 times 10 to the negative 9 meters. A lot of times we talk about these kind of distances either in nanometers or in angstroms, so we can say this is 70 angstroms. So this is, first of all, even just on an absolute scale, this is way, way larger than the wavelengths we're talking about for a baseball. In addition, if we compare this to the diameter of an atom, which is on the order of somewhere between 1 and 10 angstroms, now we're seeing that, in fact, this wavelength is significantly larger than its environment. So certainly we would expect to see that it has an effect in terms of seeing its wave-like properties. And this was experimentally validated, hopefully even more clearly than our experiment here. And at first, this was done by Davison and Germer, and they were American scientists who tried diffracting electrons from a nickel crystal. They did this in Bell Laboratories, and they found that, in fact, the electrons did diffract. And J.P. Thomson showed a similar thing. What he did was he diffracted electrons through a very thin gold foil. And this is a picture. Whoops, that is not. Okay, that is. It is a picture from your book here showing the diffraction pattern of an electron going through that gold foil. So you can see that, in fact, it's confirmed that an electron can have both wavelength and particle-like behavior. And it turns out that Davison and Thomson shared a Nobel Prize for this discovery of seeing the wave-like behavior of electrons. So this is actually kind of neat to point out because we all remember J.J. Thomson from our second lecture. And J.J. Thomson got a Nobel Prize in 1906 for showing that electrons exist and that they're particles. And it turns out that G.P. Thomson, well, that's his son. So we can actually think of this, and I'm sure this wasn't the case, but I like to think of it as a little bit of child rebelling against the father. So the father gets a Nobel Prize for showing that an electron is a particle, and the son says, well, what can I do to top that? I'm going to show the exact opposite. I'm going to say that an electron's a wave, no matter how much my father says differently, and I'm going to get a Nobel Prize for that. And he does. But the nice part of the story is it turns out they're both right. An electron is a particle, but an electron's also a wave. So father and son, happy ending. They both have their Nobel Prizes.